Welcome to section 5.5, Implicit Differentiation. And what we need to start with is comparing two different types of equations. The first is an explicit equation, which is what we've used the majority of the year and what you're typically used to using. That would be where whatever dependent variable you're using, say it's y or it could be position, whatever it might be, your dependent variable is expressed in terms of the independent variable. So y in terms of x, position or velocity in terms of time, something like that. And the bigger thing you're going to want to think about is these are equations where the dependent variable is isolated. So it's all by itself, has its own side of the equation. So ones like linear equations, quadratics, those are all situations where we would call our equations explicit. And we're going to contrast that with what we call an implicit equation, where the dependent variable is not isolated. And when the dependent variable is not isolated, we see situations like maybe the equation for a circle, maybe the equation for an ellipse, but situations where it would be tougher, if not impossible, to completely isolate our dependent variable. And so what we're used to working with, we're used to doing things like differentiating explicitly, differentiating a function that we know we can solve for y. So even an equation like this where the y is joined up with this 3x and the y is being squared, this would still be a situation where we can definitely solve for y. Y in this case would be the square root of 5x cubed minus 3x. And taking the derivative, which we can call y prime, we can call dy dx, whatever you want to use for your notation, our chain rule would yield 1/2 quantity 5x cubed minus 3x to the negative 1/2 times 15x squared minus 3. And there's just going to be one smaller issue with this, and that's if you look back at the original equation. The original equation had a y squared, so when I took that square root, I really should have been doing a plus minus. And the problem with that, this would mean that we have two different functions, and I would need to then take two different derivatives, and I'm making more work for myself. Well, we have an alternative in these situations where isolating y gets more difficult or impossible. And what we're going to use is what's known as implicit differentiation. And really this will allow us to differentiate equations that have more than one variable, which allows us to expand everything that we're able to do with our calculus skills. Because before we were locked into having y in relation to x, position in relation to time, velocity with time, but in real life, many values and problem situations are dependent on more than one variable. So let's put this new concept into play with that equation we just looked at, y squared plus 3x equals 5x cubed. And we're going to find dy dx. Picking out this notation allows us to very clearly say what we're identifying as the dependent variable and the independent variable. Y is dependent in the numerator, and the x is our independent in the denominator. And so the first step I've put down for you says take the derivative normally. And I'm going to do that over here. And it also says each time a y is involved, include a dy dx. And that's the part I'll break down after I show how this is going to look. So y squared, if we just applied power rule, we would assume its derivative would be 2y. But this direction said to add a dy dx with that. Plus 3x, well that's already a function of our independent variable, so we don't have to tack anything extra. Derivative of 3x is just 3. And differentiating the other side, 5x cubed becomes 15x squared. At this point, you might be wondering why this is even going to be necessary. Why do I need that dy dx? What's happening here? So what I'm going to do is I'm going to say y normally for us stands for f of x. So let's go ahead and imagine that y is actually a function of x. We need everything in terms of x in this problem. This would allow me to rewrite my function as f of x squared plus 3x equals 5x cubed. And differentiating this with respect to x would yield 15x squared on the right side. that 3x would still become a 3, but notice how now for this piece right here, we would have to apply the chain rule with this function of x being squared. And that would yield 2 times f of x times the derivative of the inside function, f prime of x. And all we got to keep in mind is y is really equal to f of x, and f prime of x, a secondary notation we had for that was dy dx. So substituting both of those back in will yield what we see on the other side of this blue line. The implicit part of this problem is implied that all of your variables that aren't x are actually functions of x. And now, it says because we want to find the derivative, we want to find dy dx, we want to solve for it, get it by itself. So we want to get all the dy dx terms on one side. Taking our equation, that would mean 2y dy dx would equal 15x squared minus 3. It says factor out the dy dx if necessary. That's if you have multiple terms. If we only have one term, we can jump straight down to the end and get that dy dx equals 15x squared minus 3 all over 2y. Notice this is different from what we're used to. In these implicit differentiation problems, the majority of them, our derivative, our slope along whatever curve this equation defines, will require both x and y. We're going to need the entire ordered pair in order to find the slope at that point. So let's try with these ones at the bottom. So y cubed minus 2x equals x to the fourth plus 2y. We're going to try to get dy dx. So let's differentiate each term in the problem. Y cubed becomes 3y squared. That is not a function of x, so we're going to have this notation for the derivative, minus 2 equals 4x cubed plus 2, but then again, that was a term that had a y, so we're going to have to put a dy dx there. We're going to get all the terms with dy dx. I'm going to get them to the left side, which will involve subtracting that 2 dy dx. We'll add that other 2 onto the other side. And here's the situation where I have more than one term with a dy dx, so we'll factor it out. And our final step, our slope for whatever curve this defines, will come from 4x cubed plus 2 over 3y squared minus 2. And one more before we check a couple of the application problems with this. 3x squared plus 4x times y squared minus 5y cubed equals 10. So the 3x squared will be a 6x. And notice how I said 4x times y squared. Those are two different functions of x, the actual 4x and the y that is my implied function of x. This has to be a product rule. So we'll take first times derivative of the second, and there's where my dy dx will come in, plus the derivative of the first times the second left alone. Note, no dy dx on that second term because I was differentiating the 4x, minus 15y squared with another dy dx equals 0. Derivative of that constant on the other side has to be a 0. And now we'll do some expansion here. 6x plus 8xy dy dx plus 4y squared minus 15y squared dy dx equals 0. I'll keep all my terms with a dy dx on the left side and move everything else that doesn't have it to the right. And so that would include my 6x, which would be a minus 6x, and a minus 4y squared. I'll factor out the dy dx from the multiple terms, and this one will end very much like the one on the left. We'll just divide by that big chunk that's left over here, the part after I factor out the dy dx. We'll divide both sides by that, and get our final derivative. So let's try to put this to use on something hopefully familiar. We should notice that this x squared plus y squared equals 4 is the equation for a circle. And we want to find the equation of any tangent line to that circle at x equals 1. So think about circle being centered at 0, 0, and it's got a radius of 2. Well, at x equals 1, I'm going to have 2 spots where I could have a possible tangent line. And so that's why the problem says find the equation of any tangent line there. I can find it for either the one up top or the one on the bottom. So first thing we'll do is remind ourselves that for the equation of a tangent line, we're going to need an x value, which is 1. We're going to need a y value, which is going to have to come from that equation. And so instead of x, we're going to have 1 squared plus y squared equals 4, which would make y squared equal to 3. And our y value could be plus or minus square root of 3. And there's that situation where we could end up with 2 different tangent lines. And now we just need the tangent slope, which we've always kind of just denoted as f prime of 1. But in this case, where we don't have an explicitly defined function, we're going to say dy dx, and in subnotation, 1 comma square root of 3 to talk about the slope at that point. Or if you want to use negative square root of 3, that'd be fine as well. Big thing is we need our derivative. So we'll differentiate this implicitly, and the derivative of x squared would be 2x. The derivative of y squared will be 2y, with that dy dx tacked onto it, equal to the derivative of 4, which is 0. So, isolating our dy dx term, we will get that our slope around this circle will be defined as negative x over y. So if I want my slope, it's going to be negative of my x value divided by my y value, which will give me negative square root of 3 over 3. And if you had used the negative square root of 3, you would have gotten a positive square root of 3 over 3 for your slope. And so our tangent line will be y minus the y value equals our slope, negative square root of 3 over 3, times x minus our x value. And if you wanted the second equation you could have used, it would have been y plus square root of 3 equals square root of 3 over 3 times still an x value of 1. Either one of those would have been good. And finally, we're going to take a look at just doing a second derivative on one of these problems. Not that the application's anything too big, but since we've talked about properties of first derivatives and second derivatives, I want to show that it's possible to do a second derivative for any particular equation or problem that we may see. So the first thing that you're going to need is dy dx, where first thing we're going to need is our first derivative. So I would say, go ahead and pause now, see what you know about implicit differentiation to this point, see if you can't get the first derivative of the equation you see here, and restart the video when you're ready. And hopefully you got this. Dy dx equals 4x plus 1 over 2y minus 3. And we're going to go ahead and go for the second derivative. And on this one, hopefully you notice we're going to have to use quotient rule on it. So our second derivative will equal low d high, and again, that being a function of x, I don't have to worry about it too much right now, minus high 4x plus 1 times the derivative of the bottom, which would be 2 dy dx from differentiating that 2y, all over 2y minus 3 squared. And the only issue is this right here. We need our second derivative to be in terms of x and y. We need this out. Well, luckily we know what dy dx is equal to. So we can just do a substitution. I'm going to go ahead and do some expansion as we go across this. So we're going to get 8y minus 12 minus, I'm going to keep these ones because I still have to deal with this dy dx, 2 times our first derivative, which was 4x plus 1 over 2y minus 3. And all over 2y minus 3 squared. So you get to that point, I mean, You can do some more algebra and try to get this thing sorted out a little bit better. Maybe something a little bit more like this, where I can take that 2 and that 4x plus 1 and say I've got 2 4x plus 1 squared over 2y minus 3. And notice now we've got fractions inside of fractions, something that we never really like. And so you can follow these arrows and see what I did to kind of simplify this down a little bit farther. The biggest thing was understanding what we can't have in our final notation, and that was that dy dx term. So hopefully you're comfortable with the mechanics on this final example. If you feel comfortable with everything up through this, examples 1 through 4, and the idea of implicit differentiation, then you'll be in pretty good shape. All that's left is for you to go ahead and try to practice this, because the next section is going to show the larger implications of this idea. So please make sure you get plenty of practice in. Don't forget to review and summarize your notes, and thank you for watching.